All right, we're recording. And it just recorded me saying we're recording. And now it just recorded me saying that it's recording. Anyway, I can't do that. It's too many times. So we are starting our new unit, and this is section 8.1, arc length and surface area. Last year, because these are not AB topics. Did you guys do these last year, though? Did you do both arc length and surface area? Oh, nice. Arc length usually happens during AB. Surface area, not often, though. So, interesting. You guys are awesome. All right, so let's do it. Arc length and surface area. Let's just start with arc length. Arc length. So let's say that we want to find the length of this beautiful arc. Well, just like we do before, if we want to derive a formula for it, we can cut it up into parts and then, put more and more parts in the thing and then find that limit and yada, 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 kind of like we did with area. So this is arc length, though. So if I were to cut this up and approximate using line segments, that's where the formula comes from. So I'm going to put this first point as x sub 0, y sub 0. The next point is x1, y1, and then x2, y2, and finally x3, y3. And we're going to find the length of each line segment. I don't really have room to label on here, but I'm going to call them the line segments L1, L2, and L3. So if I want to find the length of L1, that first line segment, it's just using the distance formula. And remember, the formula then is the square root of, in this case, it would be x1 minus x0 squared plus y1 minus y0 squared. And then L2, similarly, L3, similarly. So L2 square root of x2 minus x1 squared plus y2 minus y1 squared. And then L3 is the square root of x3 minus x2 squared plus y3 minus y2 squared. So that would be the length of each individual line segment, and then if we add them up, that's the approximation of our arc length. And, of course, the logical letter to choose to stand for arc length is S, because there's not an S in the words arc or length. I'm sure it has something to do with a different language. I don't know. Anyway, S is kind of the standard letter we use for arc length in formulas, and it'd be the sum of those. Now, I'll just jump ahead. Let's just say we can use a summation to represent it. And actually, I should say approximately. Arc length is approximately equal to the summation as I goes from 1 to 3 of the sum of all these line segments. So I'll say L sub I. But now let's start turning this into our arc length formula. So I can see that this would be, as I goes from 1 to 3. If I look at this, I can write this a little differently instead of saying the difference of the x's and the difference of the y's. I can just use delta x and delta y. So I'm going to say the summation of delta x sub I squared plus delta y sub I squared. So I know I'm putting a lot of stuff down here really fast. Let me stop right now. Any questions so far? Because now we can say that the arc length is actually equal to, if I can break this up into an infinite number of line segments. So I'm going to say the limit as n approaches infinity of the summation as I goes from 1 to n. And I'm also going to start playing around with the argument for this summation a little bit. First, I'm going to factor out a delta x sub I squared. So it will become 1 plus delta y sub I squared over delta x sub I squared. And that's still times that delta x sub I squared, and that's still in the square root at this point. I'm just factoring out of the radicand. And then I'm going to do a couple other things here. Arc length is the limit as n approaches infinity of the summation as I goes from 1 to n. That delta y sub I squared over delta x sub I squared, I can just take the squared out, square the entire fraction, and delta y over delta x. Why, that sounds like slope. And we know in calculus, something else to represent slope is the derivative. So I'm going to make a little jump here and just say that second term in the quantity is f prime of x squared. And then we still have the square root of delta x sub I squared. Square and square root will cancel out. So then we have just delta x sub I outside of the square root. And now this looks like a Riemann sum that we can rewrite as a definite integral. And that's where we get our formula for arc length, which is the integral from a to b of the square root of 1 plus f prime of x squared dx. And that is arc length. Yay! So any questions about that? So that's where the formula comes from. Now we know. Let's just do a problem, and then we'll move on to something a little more fun. Surface area. Yay! So example. Find the arc length of y equals x squared minus 1 over 8 times the natural log of x on the interval (1 to e). And I mean, it's pretty much straightforward. You just plug it into the formula. Most people, I'm guessing Miss Peck probably did this last year too. It's a little easier if you work on the integrand separate from the integral. In fact, actually working on the radicand separate from the integral. Work on simplifying that before you actually plug it into the formula. Did she do that? Do you remember? Yeah, it's usually, I mean, depending on how straightforward your function is. This function's a little wonky, so yeah, let's go ahead and play around with this first. So we got f of x is x squared minus 1 over 8 natural log x. So then we'll find the derivative. F prime of x is 2x minus 1 over 8x. And then we get to square that. Yay! So just kind of working it out in pieces. So let's see, that would be 4x squared minus 1 half plus 1 over 64x squared. Double check me on that. That looks nothing like a 4. We okay with that? And then 1 plus that, 1 plus f prime of x squared. Well, that 1 is just going to get added to the negative 1/2. So it's going to turn that middle term into a plus 1/2. Yay! So we can go ahead and start working on our integral. So any questions about that? Anybody notice anything? This doesn't always happen, but it's something to watch out for. Joshua?
If you took it back down to the square root, it would be no, it would be because it would change from the f times x from negative 1 over 8x to positive 1 over 8x.
Exactly. Yeah. Remember, we're going to have to take the square root of this eventually. So it's nice if you get something inside the radical that is squared, so you can easily take the square root of it. And look at this compared to this. The only difference is this plus sign and minus sign. And so this will factor into something squared. We can see it right now. 1 plus the square root of f prime of x squared is 2x plus 1 over 8x squared. So do you guys see that? It's going to make life a lot easier when we plug into the radical. Remember, it's because we squared this, if we see it visually. We squared up here to get this, and the only difference is this minus and plus sign. That means this minus is plus. So, when we plug into the integral, oh, life is so much easier now. Any questions so far? Yes? Yeah. And like I said, it doesn't always happen, but just be on the lookout for stuff like that, because it happens often enough. All right, so if I plug into the formula for arc length, my limits are 1 to e, and it's the square root of 2x plus 1 over 8x squared dx. You don't have to have the squared and the square root, just for purposes of the notes, to kind of visually see it. So it just becomes this, which is now pretty easy to integrate. Yay. Any questions there? Let's keep going then. Welcome back. Let's do some calculus. Yeah. All right. What's the antiderivative? Come on. Well, actually, I was going to say even my AB students should be able to do this, but actually they don't know natural log yet. Oops. We're in the unit, though. They're going to learn it now, so they will. All right, so we get x squared plus 1/8 natural log of x from 1 to e, and then we'll just keep going. Plug in the e. We get x squared, or e squared. The natural log of e is 1, so it's 1 times 1/8. And then it's minus 1 squared, which is 1. Natural log of 1 is 0. So that'd be 1 plus 0. So it looks like the arc length is e squared minus 7/8. Who needs a calculator? We don't need no stinking calculators. Any questions about that? So the idea of arc length is pretty straightforward. It just is as complicated as whatever this is, really. All right, let's do surface area then. I should have asked if anybody remembered the formula for arc length before I gave it away. Did you guys remember the formula for arc length? Well, now you do. Yeah. Do you guys remember the formula for surface area? We'll look at it. Oh gosh. Oh golly. We're going to derive this one. And I'm going to start from the very beginning with this. So, surface area. Specifically, we're going to look at surfaces of revolution. All right. To do this, we're going to go back to the very beginning. We're going to go back to pyramids. Yeah. Let's look at a square pyramid first. Should make that bigger so that I can label stuff. So we got a square pyramid. Pyramid. So it's got these edges on the base. I'm just going to label those with a lowercase b. And then if I want to find just the lateral area, and remember the lateral area for a pyramid is going to be everything except the base. That's all the lateral sides, so the side area. These are just triangles though, and because it's a square pyramid, all the sides are going to be the same. They're all triangles. To find the area of a triangle, it's 1/2 the base times the height. So we have the height of the triangular face, which is also known as the slant height. Slant height. And what's the standard letter that we use for slant height? Can't use S because that arc length got that one. So we go to the next letter, L. L for slant height. I don't know who came up with these. So the lateral area, which for the rest of this I'm just going to abbreviate as LA. It's just 4 times the area of each one of those triangles, which is 1/2 the base times the slant height. And if I just rearrange stuff a little bit, I'm going to put the 4b together. What does the 4b represent on my pyramid? Do you see it? It's the perimeter of the base. Yeah. So for pyramids in general, we actually say that the lateral area is 1/2 PL, use a capital P, where that capital P is the perimeter of the base. So I started off with a square base, but we really could have a pentagonal base, hexagonal base, yada yada base, and so on. We could have 10 sides, 20 sides, 40 sides. We could have an infinite number of sides. If it was an infinite number of sides, what would the shape actually be? It'd be a cone. So now I'm going to take this to a cone. So any questions just where that 1/2 PL comes from? All right. So now let's look at a cone. Cone. Now cones still have a slant height. So that's L. And of course they have a radius. This is a cone. So the lateral area for a cone, lateral area, oh, that's the wrong green. That's 2. There we go. The lateral area for cone is, we can still call it 1/2 PL, but now we're talking the perimeter of a circle. So that's just 1/2 times 2 pi r L. So the lateral area for a cone is just pi r L. Ah. All right, how is this going to be used in surface area of areas of revolution? I don't know. We're almost there, though. But any questions now? Yes, Joshua. Ooh, yes it will. Nice. Very, very nice. Before we get there, though, we're going to look at one more shape, which is, now we're going to take this cone, and we're going to cut off the top, and we're going to have a frustum. I know, right? So it's going to look like this. I'm still going to draw my cone. Boop, 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 boop. Yeah, I got enough room. And like I said, I'm going to cut off the top of it. And so I'm actually looking just at that yellow area. And that will be a frustum. Rawr! Yes. Whoop. Is that enough right there? Oh, that's actually all there is, huh? All right, so because I'm focusing on the frustum itself will also have a slant height. So from here to here is the slant height of the frustum. But I think we can see that to find the surface area of the frustum, we're going to look at the surface area of the big cone, and then take, or I should say the lateral area of the big cone, and then take off the lateral area of the little cone. So I do need something on that little cone. So I'm going to label that slant height as L1. And then we definitely have 2 radii here. So I'm going to have the radius of the little cone and the radius of the big cone. So let's call the radius of the little cone R1 and the radius of the big cone R2. R2D2. Ah. Boba Fett. Have you guys watched Boba Fett? Any Star Wars fans in here? Okay, a couple. Really? Just 2? I actually haven't seen it because I'm watching it with another couple, me and my husband, and it's not because my husband falls asleep. I can't blame this one on him. Oh my God, that just was recorded. Don't tell him. But but they actually have COVID, so we took this week off. Well, actually, they probably do. They're waiting for test results, but they're symptomatic. But we're gonna, whenever they get better, we're gonna do it. What? No, it's actually if I hit that, it'll go back. You'll see. Anyway, yeah. Where was? Oh, yeah. Let's find the lateral area of the frustum. Okay, so the lateral area of the frustum. Lateral area of the big cone minus the lateral area of the little cone. Boy, say that 10 times fast. Like, what did I even say? Lateral, right? Lateral area of the big cone minus oh, no, not even going to try it. Okay, so we got the big cone. Big cone has pi R2L. But is it L? No. The big cone, actually, the slant height is the whole entire thing. L1 plus L. I'm looking at the whole entire cone. Minus the lateral area of the little cone, which is pi R1 L1. Now this is going to get a little funky. So first I am going to distribute, and say pi, let's keep track of all these subscripts, R2 L1 plus pi r2L minus pi r1L1. So I've just distributed across the quantity there. And then what I'm going to do, these two terms that have the L1, I'm going to factor out the pi and the L1. So I'm going to put them together but factor out also. So it's going to look like this. It's going to be pi, and then I'm going to do the R2 minus R1 inside L1. And then we still have the plus pi R2L. So I have that. So any questions what I did there? So what can we do with this? You know what we can do with that? We can take a break from that. Let's go back actually to the picture. Using similar triangles. There's a relationship between all the L's and the R's. So we have the big cone, the slant height of the big cone to the radius of the big cone is equal to the slant height of the little cone to the radius of the little cone. And then I can cross multiply. Here, wait, I'm just going to do that. Okay. Cross multiply, so we have R1 L1 plus L equals R2 L1. And actually, for sake of space, I'm going to distribute that R1 across everything. So I'm just going to do that right here. Whoops, not that. There's a glare and I can't quite see. R1 L1 plus R1 L. And what I'm going to do now is put the things with the L1s on the same side of the equals. So I have R1L left on the left-hand side. And I will have R2L1 minus R1L1. And then on that right-hand side, I can factor out the L1 and have R1L equals R2 minus R1 L1. Why the heck did I do that? But any questions of what I did there? Because now this can actually go. I have some substitution. Oh my God, I can't say words anymore. I can substitute. So the lateral area for this frustum, I can now say is pi, and then that part that I underlined in blue highlighter is R1L plus pi R2L. I'm almost there. Trust. And now there's a pi L that I can factor out. So if I factor out the pi, I get this. And then, for the grand finale, that's not really the grand finale. Still have to get the formula for surface area. This is just the frustum. If I call R with no subscript the average of the radii, that means that R is equal to R1 plus R2 over 2, or I could say 2R is equal to R1 plus R2, and oh my gosh, look, I have an R1 plus R2 in this formula. So I can write the formula as the lateral area is pi 2RL, or you typically see it as 2 pi RL. R is the average of the radii of the frustum. L is the slant height of the frustum. Now I know I could have just given you the formula for the surface area, lateral area of a frustum. That wouldn't have been any fun, though. Now you guys know how to find it. But any questions about that? Yeah. You see it? Okay. All right. Any other questions? Okay. So now we're going to do what Joshua talked about. We're going to take our surface area of revolutions and we're going to cut those up into frustums using this formula, and then we can derive the surface area formula from that. Is that enough there, Joshua? Okay. All right. So let's look at that. Areas of surfaces of revolution. Nope. Yeah, I know there's a little pause there. The pause is, if I hit pause, then it will be paused. All right. Lost my train of thought. All right, anyway. Let's imagine if we take this lovely curve, rotated about the x-axis. It's going to look like a vase on its side. So what I'll do, imagine if we put a whole bunch of frustums, which are going to be formed by basically cutting a line segment, cutting the arc into line segments. But then as these arcs rotate, we can see that they're going to make a frustum. So let's look at the surface area of one of these frustums. And we're just going to kind of jump right into the formula. So the surface area, the idea is, just like we normally do, the idea will be to fit an infinite number of frustums into this picture. So the frustum's going to, like the one base of the frustum and the other base, they get closer and closer together until they're basically the same base. So the two radii essentially become one radius. So if we just look at the radius of this frustum, you can think of it as the average, but again, as they become infinitely thin, it's really the same radii, their same radius. So the surface area, I'm just going to jump right to it. It's that 2 pi RL. So it's essentially this. But let's go ahead and put this a little more formally, but then we're really going to put it formally. Actually, I'm going to put the 2 pi out in front. So the radius is going to be measured from the function to the axis of revolution. So that's going to be a function itself. I'll just call it r of x. And then the slant height of this, when we turn it into the integral, it's really the sum of all the slant heights. But the sum of all the slant heights is really like the arc length of this picture. And that's really what it is. So we actually use the formula for arc length that we had before, which is the square root of 1 plus f prime of x squared dx. And that's the formula. So if you think of it in terms of 2 pi RL, 2 pi, r is the radius, L is the arc length. So now let me put this more formally. Lots of words on this one. Get ready. And then we'll look at an example. And we'll have an example we're going to do in 2 different ways, and then that's it for the notes. Yay! Any questions so far, though? Alrighty. Bored with those colors. Let's go teal. Alright, surface area. Of volumes of revolution. I know I'm saying the word volume, but we're not actually finding volume, we're finding surface area. So this one is going to be helpful if we have like the more detailed wording. So that's why we're going to write a bunch of stuff out. Let y equals f of x have a continuous derivative on AB, the area S, capital S, of the surface of revolution formed by rotating the graph of y equals f of x about a horizontal or vertical axis is. And notice it says horizontal or vertical, because you're going to see we can make these a dx or dy problem. It doesn't matter which way the picture is oriented. So you do whatever's most convenient. Surface area is 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x squared dx, where r of x is the distance between the graph of f and the axis of revolution. I'll let you get caught up there because we got more. It's going to be a big, big cloud. But don't worry, I'd say we're about 2/3 of the way with the writing for this cloud. So this is if it's a dx problem. If you want to make it a dy problem, how do you do that? Well, I'll tell you. If x equals g of y on the interval c to d, then the surface area is s equals 2 pi c to d r of y times the square root of 1 plus g prime of y squared dy. Again, where r of y is the distance between the graph of g and the axis of revolution. Whew. Stretch out that hand. We should all be writing with fountain pens. Fountain pens actually train your hand to have a delicate touch. You don't want to push hard. Some countries actually make students, they still do it, make students learn to write with a fountain pen for that reason. I actually like collecting fountain pens. I have some glass pens. Like they're literally all glass. Even the tip, what you write, you dip it in ink and you write with it. It's pretty cool. I'll bring him in. It's like, whoa, you can write with ink, with the glass. And actually you can write several lines before you have to dip the glass in again. Anyway, all right, let's look at an example. The last example. Anybody still need this? Here's the example if you want to start thinking about it. Find the surface of revolution formed by rotating f of x equals x squared on the interval 0 to root 2 about the y-axis. And so we'll do this both. We'll make it a dx and a dy problem. And we will see that, dang it, we're going to get the same thing. It'll be like magic. Ooh, speaking of magic, anybody see the Harry Potter reunion? That was actually pretty cool. I was expecting it to be like really, honestly, kind of lame. It was kind of fun. And did you see the scandal about it? They used the wrong picture of Emma Watson as a child. It actually wasn't Emma Watson. It was Emma Roberts, another actress. They fixed it apparently, so you can no longer watch it, but you can see screenshots of the picture. I tell you, man. I should put this on a new page. Anybody still need the old one? I'm gonna go to a new page then. I tell you, man, if life was that, if that was the most scandalous thing, they used the wrong picture of somebody. And it's actually an adorable picture. It's just too bad it wasn't Emma Watson. Wouldn't life be great? Here's my answer to when you get the world leaders in a room and they're trying to agree on something, they're trying to get them to talk to each other like human beings. Everybody's got to wear a silly hat. I think that could work. Can you imagine Donald Trump, actually, let's say Joe Biden and Putin, both trying to talk to each other while they're wearing goofy hats? I want to see that. Silly hats, goofy hats. That's not a goofy hat. I mean, I got goofy hats in there. I want to see them wearing that. Anyway. All right. Let's do this thing. Let's draw a picture. It always helps to draw a picture to have a visual. Zoop. We know y equals x squared parabola. If this is the square root of 2, the y coordinate's got to be 2. And it says rotating about the y-axis. Ooh, that's not even close. That's a little better. So we're talking about this bowl shape. Finding the surface area of the bowl. Now, as far as the representative rectangle in this goes, it's going to help if we make the representative rectangle be the radius of this area of revolution. So measuring from the axis of rotation to the graph is your radius. And I'm just going to label it R, not R of X, R of Y, because like I said, we're going to make this both a dx and a dy problem. Because you may be thinking, wait, looking at that rectangle then, that would have to be a dy problem. But you can actually think of this as a dx problem also. We can do it both ways. I will show you how to do it. What do you guys want to do first, dx or dy? Dx. Oh, sorry. Majority, I think, said dx. I'm going to go with that. Let's use a different color. dx problem. All right, so dx, everything's got to be in terms of x. So our function already is, we have f of x equal x squared. And if we think of the formula, we're going to have to do the derivative and the derivative squared. And that's not that big a deal on this one. This would be one of those, you could probably just put it right in there. There's that. Excuse me. Now our R of X. Our R of X is measuring horizontally, so we are going to think of right minus left, which may seem a little weird, because right minus left, we've usually used that when it's a dy problem. But our rectangle is going horizontally, so it is measuring a horizontal distance. So we do want to think about right minus left. It's just, we're going to put the right function and the left function in terms of x. So what do you think, looking at the picture and where that rectangle is that represents the radius, what do you think we're going to use to represent the right part of the radius? This is where it can get a little weird. We are, yeah, it's x. Because if this is a dx problem and we want it to correspond to x, this value will just correspond to whatever the x coordinate is on the function. And what's the left? What's the x coordinate? Yeah, it's just 0. So we can say that R of x is x. So, now if we plug into our formula, 2 pi r L. And what are my limits going to be? 0 to root 2. Look along the x-axis. And then we work that out. So any questions just first on the setup of this? I'm going to go grab my calculator. We can actually pretty easily solve this, though. Anybody know what technique we use to solve it? Yeah, just use sub. Look at the derivative of the inside of the radical. It'd be 8x. We have the x. We don't have the 8. So this wouldn't be that hard to use u sub. Yeah, Lilith.
Where, like, how do you then visualize the dx on the graph? Like, where are the little intervals?
So the dx is actually, if we go back here, so it's not, the representative rectangle in this case is not going to tell you the dx or dy. It's just helping you figure out where r is. The dx is going to, we'd actually have to go back here. Where is it? Here. So the dx isn't, it's not really, you can't really see it on the picture necessarily. The dx is coming from the arc length part of the formula. And remember, in the arc length part of the formula, it ended up coming from, like, you know, we had this, and then we factored out the delta x squared, and then that was here, that became our dx. But where is this? You can't really represent it anywhere here. It doesn't, and it's because it's just kind of the way we derived it. So it doesn't really have a representation on the picture. That's a good question. Any other questions before I just plug this into the trusty old calculator and see what it is? All right. So what I'm actually going to do, I'm not going to do the pi. I'm going to save the pi out because this actually ends up being a pretty nice fraction. I just forget what it is. So I'm going to do 2 math 9 from 0 to root 2 of x times the square root of 1 plus 4x squared dx. So that's 13/3, and then I'm just going to put the pi with it. Whoops. So s is 13 pi over 3. But like I said, we could easily do this by hand using u sub. It wouldn't be that hard. Let's see if we can actually get the same thing with a dy problem. Any questions on that? All right. Does anybody still need this before I look at it as a dy problem? Actually, maybe I'll just do the dy problem here. dy problem. So this time we're going to have g of y. What's my g of y going to be? If y equals x squared, then x equals root y. And then g prime of y, it's going to be 1 over 2 root y. So g prime of y squared is 1 over 4y. Y. Now let's look at our radius. R of y. We're still talking about the same exact picture, and the radius is still going horizontally. So we're still going to measure right minus left. And if we're going to do that, what do you think we're going to put for the right function this time? You can still think of it as x minus 0, because it still is the same radius. However, we have to put things in terms of y. So the x coordinate is going to be root y, because the function is x equals root y. Or we can just say root y. Well, root y minus 0 is root y. So it's a subtle thing. So when your radius is going horizontally, you're going to use x as the coordinate. If it's going vertically, then the height of the radius changes. That goes along the y-axis. But now that we have this, it'll be easy to set it up. So this is really the key. Any questions here? So surface area is 2 pi. What are my limits of integration now? Yeah, 0 to 2. This time I'm looking on the y-axis. So 0 to 2. R of y times the square root of 1 plus g prime of y squared dy. And this one would be pretty easy to do by hand also. Anybody know what we would do here to do it by hand? Do you see it? While you guys are looking at that, I'm going to start plugging it in. Do you see it? Multiply it out. They're both in square roots. If you distribute that y inside the radical, you're going to get y plus 1/4. It's just u sub again. And you don't even really need the u sub because the derivative of the inside is just 1. But anyway, 13 pi over 3. So different ways of setting it up. Any questions about that? All right.